Okay, in this lesson, we're using trigonometric ratios in basic applications. Now, in your guided notes book, this is on page 24. I know I feel like we're skipping around a bunch in this trig section. It's a little out of order. So page 24, that's where you're headed, and it has just these 3 problems on here. And very similar to our application problems with similarity, we're going to draw a diagram, we're going to make sense of it, solve, and then write our answer in a sentence to interpret our solution to make sure that it makes sense. So let's just look at a couple of the little terminology language that's used in trigonometric applications. The first one is in reference to the angle. So whenever we do trigonometric applications, there is some sort of object, right, that is high or that is lower than something else. And we have what we call a line of sight. Line of sight is like them looking at the object. So here's my line of sight, looking at the object. You also have like your horizontal line of sight. If you were to look straight, that's kind of like this own line of sight here, right? And then you look straight up, and when you do that, you create some sort of angle. If you had to move your eyes up, and we're going upward from the line, our original horizontal line of sight, then it's called an angle of elevation. If you are like laying on this cliff here, yikes, and you're looking down to look at the boat, this is called an angle of depression. Okay, so I don't love this initial diagram up here. There's kind of different things. Technically, if this little guy isn't laying on the ground, his horizontal line of sight is about right here. So the angle of elevation would actually be this guy right here. And you'll notice when we use that horizontal line of sight related to the new line of sight, when you look up, it creates a nice 90-degree angle right there, which creates a triangle so that we can use trigonometry. Essentially, this horizontal distance is pretty easy to measure, and the angle, we can get a contraption and measure our angle, which allows us to measure something that is like a hot air balloon in the sky, which we definitely can't just use a measuring stick for if it's that high up. So then we can use like a trig function if we know a reference angle, and we can find the side opposite if we knew the distance away, that sort of thing. So that's our goal with applications. You do need to recognize though that would only help us find part of the distance here, so you would have to like add in the height of the observer if the individual is standing up. So we would want the height of the observer where they're measuring from. This angle of depression, again, let's draw a little guy laying right here. So again, he looks like he's laying down because his line of sight, it looks like horizontally is here. His new line of sight is towards the boat. So we've got this angle of depression here that we can use. I want you to notice with an angle of depression that it does create 2 triangles essentially. So we could look at this as this triangle here on the top with a right angle here. Or you can think about this as a right triangle where the cliff is the left side and the boat, the distance on the water is that like horizontal change. So we can think about it as a right triangle here. Essentially, these are similar triangles. They're going to be the same thing. We just have to make sure we use the right angle with finding the parts that we want to find. Okay, so angle of elevation, angle of depression, that's going to be the biggest vocabulary that will be new today. So let's try it a few times. So example 7 says a nursery plants a new tree and attaches a guy wire to help support the tree while its roots take hold. If the guy wire is staked into the ground 10.5 feet away from the tree. So I'm going to draw a guy wire. That's where I'm going to start before I even try to read this whole thing. So here's a tree. They plant this new little tree. And here's the ground. There's some grass. And it says they're going to attach a guy wire to support it. And it's staked 10.5 feet from the tree's center. So here's my little guy wire down here. And it's going to be 10.5 feet away. Okay, so there's a little wire attached to this thing. And it looks like it's going to attach 6 feet up the tree. So here's the wire that's going to hold the tree in place. And we're going to be about 6 feet up that tree. It asks, what is the angle of elevation of the guy wire? So again, remember angle of elevation, if the ground is my horizontal line of sight, then this would be my angle of elevation here. So let's call it theta. Theta just represents any angle measure, right? So notice if I'm looking at that and I want to use some trigonometry, if I want to find an angle, then I use the opposite in relation to the adjacent here, which is TOA, or tangent. So I would set this up and say, well, the tangent of theta is equal to 6, the opposite, over the adjacent. And once I have that, again, if I'm solving for an angle, then I do the inverse tangent of 6 over 10.5. Okay, so I'm going to go to my calculator and do the inverse. That's not my calculator. That says we're currently recording. So we do inverse tangent, so second tangent of 6 divided by 10.5. And it said round to the nearest degree, so 29.74. We're going to round that. Oh, not that one again. To, oh, bell rang, distracted me. Excellent. Theta is about 30 degrees. So if we're interpreting that, that means that the guy wire makes a 30-degree angle with the ground, or is rising at a degree of 30. Awesome. Okay, let's try another one. Again, the hardest part is just drawing the little diagrams so that we find the right pieces. This one says a NASA recovery helicopter hovers 75 feet above a space capsule. So let's draw that first. Okay, I am not an artiste, but we will do our best. So here's a little helicopter. Whoop. We'll give it some things up here that are, and some things back here, right? That looks kind of like a helicopter where the pilot sits here. Excellent. There's a helicopter. Give him some little leg things. And he's hovering above a space capsule. So this is like a recovery capsule when the astronauts come back from space. Oh, mine looks like a UFO. And it's 75 feet above that. So here we go. Hovering 75 feet above that. I guess I didn't need to go into the space capsule. If the angle of depression to the recovery ship, now I'm guessing that we're in water because there's a ship here. So here's the recovery ship, and it's going to look like a sailboat because that's what I can draw. Again, the angle of depression to the recovery ship is 40 degrees. So I want you to just think about the line of sight because this just helps me draw my angle. So here's his horizontal line of sight. So if he's looking down at the recovery ship, this angle of depression, I just happened to draw it from the bottom of the helicopter, yikes, is 40 degrees. And then it asks how far is the ship from the space capsule. So you can either, again, think about this top triangle and find this distance, or you can go here and find this distance, right? Because it's asking how far is the ship from the space capsule. So let's just think about this bottom one. So we're finding this down here. And if this is 40 degrees up here, you can do this two ways. You can see that this makes a 90-degree angle. So if this is 40, this must be 50. Or because these are like parallel lines, this one down here is 40 degrees. So either way works. I'm going to call this one up here 50 degrees and let that be my reference angle. So it looks like I want to find side opposite, and I know what this adjacent leg is. So again, this is tangent. Tangent is very common in our application problems. So we set up tangent of 50 is equal to x over 75 feet. So then we go ahead and we solve that. We multiply by 75. And x is equal to 75 times the tangent of 50. And if we do that, let's set that up, 75 times the tangent of 50. So about 89.4. So this means that the recovery ship is about 89.4 feet from the capsule. Okay, let's do one more. Your school building is building a raked stage, which is a stage that slants upward from the front to the back to give the audience a better view. The stage will be 30 feet long and from front to back with a total vertical rise of 2 feet. So here's a stage, and it looks like it's going to be 30 feet long, and it's only going to rise 2 feet. So my diagram is probably really off, but That's all right, as long as we've labeled them correctly. And it looks like you want to rake, or the angle of elevation, to be 5 degrees or less. So this angle right here on the left needs to be 5 degrees or less for safety reasons. So we're going to determine if the raked stage is within our desired range. So we don't know the angle, but we want to see if what it is so we can decide if it's safe or not. So let's call it theta. Again, if I'm looking at that as my reference angle, then this side over here is leg opposite, and here's the hypotenuse, so we're going to use sine. So the sine of theta is equal to 2 over 30, and if I'm solving for theta, we use the inverse sine. So we do the inverse sine of 2 over 3, second sine, 2 divided by 30, and we get about 3.8. So theta, or the angle measure, is about 3.8 degrees, right? So interpreting that, we would say, well, great. The angle of elevation is only 3.8 degrees. Ooh, hope you can read that. So it will be safe, because it's less than 5 degrees. Awesome. Okay, have some fun with these applications. I loved seeing your guys' pictures on your last assignment. And again, it's just a matter of really practicing with that language of angle of elevation and angle of depression. So the more accurate your drawing is, the more I feel like you're going to be able to grasp that concept and identify those heights and